What is a dot product, and how is it used? I'm Ben, this is Physics or Bust. That's what we'll get into right now. A dot product is an operation done with vectors that is a lot like multiplying, but it keeps in mind the fact that there are different dimensions, x, y, and z, that the vector is pointing in. And the end result of a vector is to get a scalar answer. There's two main ways that vectors are expressed, so we'll discuss doing a dot product with both of those ways. The first way is when you look at a vector being given with a magnitude at a certain direction. The second way is where you're given a vector by giving all three components, whether it's with I hat, j hat, k hat, or just within the bracket system. Now, given these two vectors, vector A as given a magnitude at theta 1, and vector B given a magnitude at theta 2. So the calculation you'll need to do is take the magnitude of A times the magnitude of B, and then multiply that by the cosine of the angle between the two vectors. Now note, it is not specifically adding up angle A and B or subtracting them. It depends on the situation and where those angles are. For instance, if we were given this as theta A and this as theta B, if that's how you gave the angle, or were given the angles, then you would do something like 360 minus theta A minus theta B would give you theta C. If instead you were given this situation with your vector A and theta A here, and vector B with theta B there, then the theta that you're looking for would be adding them up. But it all depends on the situation you're looking at. The theta you need in this equation to make a dot product is the angle between the two vectors. If you put them tail to tail, what's the angle between them? And that's the theta you're looking for. The main purpose that dot products are used in physics is to resolve a force into a parallel and a perpendicular force in respect to a momentum. So I'm going to do an example that includes resolving a force with respect to a momentum. So with this example, we have a ball moving in the negative x direction that's kicked with a force of 60 newtons in a direction 27 degrees above the positive x-axis. And we're going to go through finding the force parallel to the momentum and the force perpendicular to the momentum. So to find the parallel force, what we'll do is a dot product with the force and the momentum unit vector. Now, if you need more info on unit vectors, you can click into this video right here, and that's about what a unit vector is. So as with any unit vector, the magnitude of the p hat, which is the unit vector in the direction of the momentum of the ball, its magnitude is 1. So when we do this math of the dot product, it's going to be the magnitude of the force times the magnitude of p hat cosine of the angle between them. Right? So that means we have 60 newtons times 1 times the cosine of the angle between. So we have an angle going up 27 off the positive x-axis, and the momentum going straight in the negative x-axis. So then our angle is going to be 180 degrees minus 27 degrees, which gives us 153 degrees. So we have 60 times 1 times cosine of 153. So we get an answer of negative 53.46 newtons. And keep in mind that would get us the answer in the direction of p hat. So with the negative there, that means it's in the opposite direction, which makes sense given our diagram, right? Because the parallel force is going to be in the positive x direction. So that means our parallel force is going to be 53.46 newtons in the positive x direction. To find the perpendicular force, the best way is to use sine instead of cosine. So we used 153 on the previous one, so we'll use it again. Do 60 times 1 times sine 153, and you get an answer of 27.24 newtons. And that'll be in the positive y direction. So there's your answer for this problem, where the parallel force is 53.46 newtons in the positive x direction, and the perpendicular force is 27.24 newtons in the positive y direction. And as I said, there were two ways that you could be given information. If instead of being given a magnitude with directions with your vectors, you were given the components of the vectors, you'd want to go about it a slightly different way. Now you could be given the components in two different ways, where it's in the brackets, just the scalars, or where it has the scalars multiplied by I hat, j hat, and k hat. Either way, you're given all three scalars for all three dimensions, so we can go about this calculation. So setting up the problem, your A dot B, your vector A dot vector B would first set up where you have AX I hat plus AY j hat plus AZ k hat, that quantity multiplied by the B vector, BX I hat plus BY j hat plus BZ k hat. And if you distribute that, you end up getting 9 different expressions. But if we look at the first 3 expressions, if we say we're taking this AX I hat and distributing it with all the B's, these would be the first 3 expressions. But one of the neat things is that since we're looking at these I, j, and k hats as being unit vectors in the x direction, y direction, and z direction, I dot j gives you 0. I dot k gives you 0. The only parts of this that actually stay and aren't multiplied by 0 are the ones where the directions are the same. So in this first 3, the only one that stays is this AX BX. And then I hat dot I hat would just be 1 because they both have the magnitude of 1. So spreading that through all 3, we then get this form. So the dot product of vector A dot vector B is just AX BX plus AY BY plus AZ BC or BZ. And it's just a scalar quantity. There's no direction added to it. So you multiply each of those sets together and add them up, and you have your answer. So let's look at an example with this. And again, I'm going to do an example that includes looking at finding the parallel and perpendicular force on an object, because that's just how these dot products are used in physics. So here's our example. We have an asteroid that makes a close approach to Earth at an instant when the momentum of the asteroid is 3.50 times 10 to the 15th, 6.20 times 10 to the 16th, 0 as the 3 components for its momentum, kilogram meters per second. The force on the asteroid by Earth is 3.81 times 10 to the 11th, 00 newtons. And we're going to find the parallel and perpendicular force. So with this, our first task is going to be to figure out what p hat is. We're given the full momentum as a vector, but we need to find out what the unit vector in the direction of momentum is. So looking at the formulas here with p hat, we have the px over the magnitude of p, py over the magnitude of p, and pz over the magnitude of p. So we need to find the magnitude of p first. And we can do that using the the square root of px squared plus py squared plus pz squared. So putting those numbers in, we end up getting 6.21 times 10 to the 16th kilogram meters per second as the magnitude of the momentum. So each component of the momentum then needs divided by that number. So we get 3.5 times 10 to the 15th over 6.21 times 10 to the 16th, and 6.20 times 10 to the 16th over 6.21 times 10 to the 16th. So our answer for what p hat is 0.0564.9980. So now that we know what p hat is, we can go into our formula for finding the parallel force. So we have the px times fx plus py times fy plus pz times fc. So when we put in the numbers, we have 0.0564 times 3.81 times 10 to the 11th plus 0.998 times 3.81 times 10 to the 11th plus 0, because nothing was in the z direction. Which gives us an answer of 2.15 times 10 to the 10th for our magnitude of the parallel force. So to get the full vector of the force parallel, we then multiply that by p hat. So we take the 2.15 times 10 to the 10th newtons, and we'll multiply it by each component of p hat, 0.0564 and 0.998 and 0. So our F parallel then is in the x direction 1.21 times 10 to the 9th, in the y direction 2.15 times 10 to the 10th, in the z direction 0. Finding the parallel force at this point is a lot easier than finding this one, because now it's just a matter of taking the original force and subtracting the parallel force. So when subtracting vectors, when you're given all the components, you just subtract the components that are in the same direction. So 3.81 times 10 to the 11th minus the 1.21 times 10 to the 9th, 0 minus the 2.15 times 10 to the 10th, and 0 minus 0, which is just going to be 0. So our perpendicular force then is just 3.80 times 10 to the 11th in the x direction, negative 2.15 times 10 to the 10th in the y direction, and 0 in the z direction. And don't forget to put your units when you're writing these things down, especially as your final answer. If you're needing to learn more about vectors, go ahead and click into this playlist right here, and that'll get you going on some videos that talk about all the details of vectors and their operations you can do with them. Don't forget to like and subscribe, and remember, keep asking questions. I'll see you on the next video.